Okay, so let's move on and actually discuss the pseudocode for the merge sort algorithm. First, let me just tell you the pseudocode, leaving aside exactly how the merging subroutine is implemented. And thus high level should be very simple and clear at this point. So there's going to be two recursive calls, and then there's going to be a merging step. Now, I owe you a few comments because I'm being a little sloppy. Again, as I promised, this isn't something you would directly translate into code, although it's pretty close. But so what are a couple of the ways that I'm being sloppy? Well, first of all, there's, in any recursive algorithm, you got to have some base cases. You got to have this idea that when the input's sufficiently small, you don't do any recursion, you just return some trivial answer. So in the sorting problem, the base case would be if you're handed an array that has either 0 or 1 elements, well, it's already sorted, there's nothing to do, so you just return it without any recursion. Okay, so to be clear, I haven't written down the base cases, although of course you would if you were actually implementing merge sort. So let me make a note of that. A couple other things I'm ignoring. I'm ignoring what to do if the array has odd length. So if it has, say, 9 elements, obviously you have to somehow break that into 5 and 4 or 4 and 5. So you would do that just in either way, and that would be fine. And then secondly, I'm ignoring the details of what it really means to sort of recursively sort. So for example, I'm not discussing exactly how you would pass these subarrays onto the recursive calls. That's something that really would depend somewhat on the programming language. So that's exactly what I want to avoid. I really want to talk about the concepts which transcend any particular programming language implementation. So that's why I'm going to describe algorithms at this level. Okay. All right, so the hard part, relatively speaking then, is how do you implement the merge step? The recursive calls have done their work. We have these two sorted subarrays of half the numbers, the left half and the right half. How do we combine them into one? And in English, I already told you on the last slide, the idea is you just populate the output array in sorted order by traversing pointers or just traversing through the two sorted subarrays in parallel. So let's look at that in some more detail. Okay, so here is the pseudocode for the merge step. So let me begin by introducing some names for the characters in what we're about to discuss. So let's use C to denote the output array. So this is what we're supposed to spit out with the numbers in sorted order. And then I'm going to use A and B to denote the results of the two recursive calls. Okay, so the first recursive call has given us array A, which contains the left half of the input array in sorted order. Similarly, B contains the right half of the input array, again, in sorted order. So as I said, we're going to need to traverse the two sorted subarrays A and B in parallel. So I'm going to introduce a counter, I, to traverse through A, J to traverse through B. I and J will both be initialized to 1 to be at the beginning of their respective arrays. And now we're going to do a single pass through the output array, populating it in increasing order, always taking the smallest from the union of the two sorted subarrays. And if there's one idea in this merge step, it's just the realization that the minimum element that you haven't yet looked at in A and B has to be at the front of one of the two lists. Right? So for example, at the very beginning of the algorithm, where is the minimum element overall? Well, whichever of the two arrays it lands in, A or B, it has to be the smallest one there. Okay, so the smallest element overall is either the smallest element in A or it's the smallest element in B. So you just check both places, the smaller one's the smallest, you copy it over, and you repeat, and that's it. So the purpose of K is just to traverse the output array from left to right. That's the order we're going to populate it. We're currently looking at position I in the first array and position J in the second array. So that's how far we've gotten, how deeply we've probed into both of those two arrays. We look at which one has the current smallest and we copy the smallest one over. Okay, so if the entry in the ith position of A is smaller, we copy that one over. Of course, we have to increment I. We probe one deeper into the list A, and symmetrically for the case where the current position in B has the smaller element. Now again, I'm being a little bit sloppy so that we can focus on the forest and not sort of and not get bogged down with the trees. I'm ignoring some end cases. So if you really wanted to implement this, you'd have to add a little bit to keep track of when you fall off either A or B. Okay, so you'd have additional checks for when I or J reaches the end of the array, at which point you'd copy over all the remaining elements into C. All right, so I'm going to give you a cleaned up version of that pseudocode so that you don't have to tolerate my questionable handwriting any longer than is absolutely necessary. This again is just the same thing that we wrote on the last slide, okay, the pseudocode for the merge step. Now, so that's the merge sort algorithm. Now let's get to the meaty part of this lecture, which is, okay, so merge sort produces a sorted array. What makes it, if anything, better than much simpler non-divide and conquer algorithms like, say, insertion sort? In other words, what is the running time of the merge sort algorithm? Now, I'm not going to give you a completely precise definition of what I mean by running time, and there's good reason for that, as we'll discuss shortly. But intuitively, you should think of the running time of an algorithm. You should imagine that you're just running the algorithm in a debugger. Okay, and every time you press enter, you advance one line in the program through the debugger, and then basically the running time is just the number of operations executed, the number of lines of code executed. So the question is, how many times do you have to hit enter on your debugger before the program finally terminates? So we're interested in how many such lines of code get executed for merge sort when the input array has n numbers. Okay, so that's a fairly complicated question. So let's start with a more modest goal. Rather than thinking about the number of operations executed by merge sort, which is this crazy recursive algorithm which is calling itself over and over and over again, let's just think about how many operations are going to get executed when we do a single merge of two sorted subarrays. That seems like it should be an easier place to start. So let me remind you the pseudocode of the merge subroutine. Here it is. So let's just go and count up how many operations are going to get used. So there's the initialization step. So let's say that I'm going to charge us one operation for each of these two initializations. So let's call this two operations to set I equal 1 and j equal 1. Then we have this for loop. So clearly the for loop executes a total number of n times. So in each of these n iterations of this for loop, how many instructions get executed? Well, we have one here. We have a comparison. So we compare AI to BJ. And either way the comparison comes up, we then do two more operations. We do an assignment here or here, and then we do an increment of the relevant variable, either here or here. So that's going to be 3 operations per iteration. And then maybe I'll also say that in order to increment k, we're going to call it a 4th iteration. Okay, so for each of these n iterations of the for loop, we're going to do 4 operations. All right. So putting it all together, what do we have as the running time for merge? So let's say the upshot. So the upshot is that the running time of the merge subroutine, given an array of m numbers, is at most 4m plus 2. So a couple of comments. First of all, I've changed a letter on you, so don't get confused. In the previous slide, we were thinking about an input size of n. Here I've just I've changed the name of the variable to m. That's going to be convenient once we think about merge sort, which is recursing on smaller subproblems. But it's exactly the same thing, mn whatever. So an array of m entries, it does at most 4m plus 2 lines of code. The second thing is there's some ambiguity in exactly how we counted lines of code on the previous slide. So maybe you might argue that really each loop iteration should count as 2 operations, not just 1, because you don't just have to increment k, but you also have to compare it to the upper bound of n. Maybe. Would have been 5m plus 2 instead of 4m plus 2. So it turns out these small differences in how you count up the number of lines of code executed are not going to matter, and we'll see why shortly. So amongst friends, let's just agree, let's call it 4m plus 2 operations for merge to execute on an array of exactly m entries. So let me abuse our friendship now a little bit further with an inequality which is true but extremely sloppy. But I promise it'll make our lives just easier in some future calculations. So rather than 4m plus 2, this 2 is sort of getting on my nerves, let's just call this at most 6m because m is at least 1. Okay? You have to admit, it's true, 6m always is at least 4m plus 2. It's very sloppy. These numbers are not anything close to each other for m large, but let's just go ahead and be sloppy in the interests of future simplicity. Okay? Now, I don't expect anyone to be impressed with this rather crude upper bound and the number of lines of code that the merge subroutine needs to finish, to execute. The key question to recall was how many lines of code does merge sort require to correctly sort the input array, not just this subroutine. And in fact, analyzing merge sort seems a lot more intimidating because it keeps spawning off these recursive versions of itself. So the number of recursive calls, the number of things we have to analyze is blowing up exponentially as we think about various levels of the recursion. Now, if there's one thing that we have going for us, it's that every time we make a recursive call, it's on a quite a bit smaller input than what we started with. It's on an array of only half the size of the input array. So there's some kind of tension between, on the one hand, explosion of subproblems, a proliferation of subproblems, and the fact that successive subproblems only have to solve smaller and smaller subproblems. And resolving these two forces is what's going to drive our analysis of merge sort. So the good news is I'll be able to show you a complete analysis of exactly how many lines of code merge sort takes, and I'll be able to give you, in fact, a very precise upper bound. Okay, so here's going to be the claim that we're going to prove in the remainder of this lecture. So the claim is that merge sort never needs more than 6 times n times the logarithm of n, log base 2 if you're keeping track, plus an extra 6n operations to correctly sort an input array of n numbers. Okay, so let's discuss for a second, is this good? Is this a win, knowing that this is an upper bound on the number of lines of code that merge sort takes? Well, yes it is, and it shows the benefits of the divide and conquer paradigm. Recall, in the simpler sorting methods that we briefly discussed, like insertion sort, selection sort, and bubble sort, I claimed that their performance was governed by a quadratic function of the input size. That is, they need a constant times n squared number of operations to sort an input array of length n. Merge sort, by contrast, needs at most a constant times n times log n, not n squared, but n times log n lines of code to correctly sort an input array. So to get a feel for what kind of win this is, let me just remind you, for those of you that are rusty or for whatever reason have lived in fear of the logarithm, just exactly what the logarithm is. Okay? So the way to think about the logarithm is as follows. So you have the x-axis, or you have n, which is going from 1 up to infinity. And for comparison, let's think about just the identity function. Okay, so the function which is just f of n equals n. Okay, and let's contrast this with the logarithm. So what is the logarithm? Well, for our purposes, we can just think of the logarithm as follows. Okay, so the log of n, log base 2 of n, is you type the number n into your calculator. Okay, then you hit divide by 2, and then you keep repeating dividing by 2. And you count how many times you divide by 2 until you get a number that drops below 1. Okay? So if you plug in 32, you got to divide 5 times by 2 to get down to 1. Log base 2 of 32 is 5. If you put in 1,024, you have to divide by 2 10 times until you get down to 1. So log base 2 of 10,024 is 10, and so on. Okay? So the point is, you can already see this. If log of 1,000, roughly, is something like 10, then the logarithm is much, much smaller than the input. Okay? So graphically, what the logarithm is going to look like is it's going to look like a curve which becomes very flat very quickly as n grows large. Okay, so f of n being log base 2 of n, and I encourage you to do this perhaps a little more precisely on a computer or a graphing calculator at home, but log is going much, much, much slower than the identity function. And as a result, sorting algorithm which runs in time proportional to n times log n is much, much faster, especially as n grows large, than a sorting algorithm with a running time that's a constant times n squared.